In this video, we're talking about digital to analog converters. And they fit into this framework of how we view the world from a microcontroller's point of view. In the middle there, in that green section, we have our microcontroller. Our microcontroller lives in the digital domain. Everything it's processing is digital, all its data inside is digital, its memory is all digital. But it needs to connect to the real world somewhere. And the real world is analog, and digital is just an abstraction. It's various voltage scales that we say, if it's between this and this, it's a high, it's a low, this sort of thing. Now, so we need to interface to that real world. And what we do is when we're getting data into our microcontroller, we use something called an analog to digital, or ADC converter. When we're getting our digital data and putting it back into the real world, that's where we use our DAC, our DAC, our digital to analog converter. Once we do that, we can get our digital data out, convert it to an analog signal, and then do something with that analog signal to maybe control a variable or something in the real world. And that might be something as simple as sound, if we put it through a speaker and play some music for us. It might be controlling a motor or something like that. A whole lot of different options there for our outputs that we're using to control things from our digital domain into our analog domain. So we know that the real world, and we've talked about it before, is full of continuous analog signals. And microcontrollers use those digital discrete binary values, and we use them for processing. So our digital to analog converter, or our D to A or D/A, we're converting those discrete digital numbers, and we store them in binary, into continuous like. So they're made to look like they're a continuous number, but they're always quantized analog signal. So we're essentially putting out voltages that look like real-world analog signals. Now, we've talked about the reverse of it. We'll be talking about that next week, which is our analog to digital, or ADC. So we'll talk briefly about digital to analog conversion and what it looks like. And you see in this table, we've got a whole bunch of inputs there, A, B, C, and D. This is what we call a 4-bit digital to analog converter, because there's only 4 bits there. And 4 bits, it's not a very high resolution digital to analog converter at all. And because we've got 4 bits, 4 input bits, it gives us 16 to the power of 4 output bits that we've got there. So we've got 16 different voltage levels that we can represent with these 4 bits. So each different combination of these 4 bits, for example, 0, 0, 0, 0 gives us 0 volts. In this example, 1, 1, 1, 1. There gives us our 15 volts, or our full range voltage. We also have that variable there, which is Vref, our reference voltage that we use to work out what we're scaling this analog output voltage in relation to. We've got lots of different applications for digital to analog converters. Things in the audio domain, playing music through a CD player. We don't really use them much these days, but MP3 players and playing music out through our computer. It's coming from a digital domain, and it's playing on analog speakers so that we can hear it. Video, using DVDs, or on the olden days, talking about analog TV as well. Thinking about using signal generators. Well, we've got signal generators that we can use to, digital signal generators to create, for example, a sinusoidal function, or a ramp function, or a sawtooth function. All of those start in the digital domain, and then these days they're quantized, and we generate an analog-like voltage to look like whatever waveform, whatever fancy waveform that we want to actually implement.